So today we're going to wrap up our discussion of thermal resistance and then get into generation, thermal generation. So we'll go through a derivation, analytical derivation of thermal generation problem. But before we do that, let's just finish up where we left off on the last couple slides from lecture 3. And if you remember what we were talking about last time was you have this, this idea that if you have two different length scales or two different areas that are available for conduction, there's different ways that you can approximate the resistance of heat flowing across those two bodies. So we have this example here where we have two height scales. We have a 2 centimeter and a 1 centimeter or half centimeter height. And we're trying to come up with a way of understanding what the total resistance is between these things. We did decide that there's these different adiabatic and isothermal models that we can use. So let's kind of go through. Let's see. This is what we talked about: adiabatic and isothermal limit. We did some calculations, and then we decided that if you use the average area, that's the worst possible case, worst possible thing you can do. So let's go through and talk about the different resistance models and kind of put them in order in terms of how they do estimating your total resistance. So I think to help out with this, let's think about this pathological case or extreme case where we say that the height h1 is going to 0. So consider h1, the limit as h1 approaches 0, and what happens in the different resistance models that we have. Okay, so our actual resistance, we'll just call that our R. That's the total resistance from left to right. What happens to the actual total resistance as h1 goes to 0? Increases, but how so? To what limit? Yes. So R goes to infinity, right? Let's think about, lost my notes already. So let's think about the isothermal model. Right? Isothermal model is where we say that the heat immediately expands across. As h1 goes to 0, what happens there? What does resistance do? Any ideas? It's not so different from the actual resistance, right? You still are shutting off one of the two resistance, or one of the resistance pathways. So h1 goes to 0. It doesn't matter if you can have isothermal. There's no area to conduct to begin with. So our iso goes to infinity as well. That makes sense, right? What about our adiabatic? Remember the adiabatic model? We're saying essentially heat can only flow in this channel in the middle, and the rest of it doesn't participate. What happens there to the resistance? Also goes to infinity, increasing to infinity. Okay, so these three models, they bound the problem, but they all kind of do the same thing as this height. h1 goes to 0. Now let's think about the average model, RA bar. What happens to RA bar as h1 goes to 0? Does that go to infinity? So I say I'm going to take, let's see if I can draw here. I'm going to take this height here, and I'm going to make this completely go to 0, right? So this is no longer available. But my average area is what? It's the integral of this piece and this piece, right? So is my average area 0? No. So is my resistance 0? No. So RA bar goes to some value that is less than infinity. Right? It's a terrible infinity. Infinity, come on. Some value, it's a finite value, right? So that's wrong, right? It's wrong, that model's entirely wrong in that regard. All right, let's talk about one more model. So I'll just clear this page. So there's one more model that people use, and it's we've been thinking about heat that's flowing in varying areas as you're flowing along the path. But what if you have a situation as follows, where you have, let's see if I can draw this. So we have some channel where heat is flowing, it's adiabatic, top and bottom. So heat's only flowing in this positive x direction. And we have now, instead of a varying area available, we have a varying length between the left and the right boundaries. So that might look something like this, right? So here on the left side, it's like that. And then on the right side, you maybe have something like this. So there's a model that says, OK, let's take the average length, where if I take the average position on the left side and the average position on the right side and say this is L bar. Right? I'm going to take L bar, and I'm going to compute the resistance using L bar. So how would I write that out? I'll just say R L bar is equal to L bar over K AC, where AC is going to be, what? Let's say this is some cylinder like this. So this is the cross-sectional area that's available for heat conduction. Right, I mean, conceptually it makes sense. You're saying I don't have a single length, but I can take the average of the lengths and then compute the resistance. So just to give you a formula of how to actually compute L bar, it would be L bar is equal to the area integral, which is 1 over A times, 1 over A times the integral over the area basis of L dA, right, where L is a function of the position at any point, say in this vertical coordinate. So we have an area integral that's giving us L bar. So what's the problem with this model? Right. Think back to like an electric circuits analog, where what would happen if I have a bunch of wires, and the wires are all different lengths, and I have the same voltage applied to all the ends of the wires. But maybe one of the wires is basically going to 0 length. What is that? What would we call that? Short circuit, right? So you can short circuit heat transfer just in the same way you can short circuit electricity. And if that happens, right? So if we say at some position L goes to 0, then what happens to our heat transfer? Again, so we're saying over here on the left, this is being held at TH, and on the right, this is being held at TC. So we have fixed temperatures. That's not changing. So what happens to our, first of all, what happens to the resistance for this model, RL bar? Or sorry, let me just erase that. So what happens to the actual resistance R if L goes to 0? It goes to 0. Right, so R goes to 0, which means what? Q dot goes to infinity. However, if we use this RL model or RL bar model, that's not what it tells us, right? So we essentially miss out on this characterization of a short circuit in the heat transfer because we're not really accounting for where the heat actually wants to flow in these models. Okay, does that make sense to everybody? Any questions on that? Okay. All right, so just to wrap this up, what I want to do is give you like a hierarchy of the models. Let's see if I can each. A hierarchy of resistance models. Okay, so let's say we have our actual resistance R, and I want to decide which models give me higher or lower resistance. Let's first consider the adiabatic model. So does the adiabatic model, remember where part of the area is not participating, is that adiabatic model overestimating or underestimating the resistance? It's overestimating the resistance, right? So R is less than or equal to R adiabatic. What about the isothermal model, where all areas immediately available? Is that over or underestimating? Exactly. So now we have R iso. Okay, but we have these other two models. We have the average length model, and we have the average area model. So if you think about it long enough, we'll decide that our L bar overestimates even the adiabatic model in terms of resistance. Right? We're overestimating the resistance in this situation because there's shorts that aren't being accounted for. On the other hand, the average area model underestimates even the isothermal. Right? So if you have to rank where your resistances are going to be compared to the actual resistance, this is kind of the order that they're going to end up. Okay. All right, so that's kind of the, as far as we'll go on resistance, I think you have stuff you're doing on the homework with this. We will not be done with resistance at any point throughout the semester. This is always going to be a toolbox that we come back to and use. It's really useful, like I said, for just bounding problems, for getting quick estimates without having to do a lot of work. But as long as you kind of understand the limitations on these approaches, some of them can be useful in some situations. Okay?